Welcome viewers, in this video we'll see the single tuned coupled circuit. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic, single tuned coupled circuit. We know that coupled circuit is nothing but inductance. It is inductively coupled together. In that, single tuned means the capacitor is connected at the secondary side. It's called single tuned. This capacitor is connected in both primary and secondary side. In order to tune the circuit is called double tuned circuit. So this is coming under single tuned circuit, capacitor connected only at the secondary of the circuit. Let us consider this is the parallel resonance circuit having primary and secondary coils are available. The parallel resonance circuit on secondary is inductively coupled to coil 1. These two coils are inductively coupled. The coil is excited by the source Eg. The primary coil is excited by the Eg. Rg be the source reactance. Rg is the source reactance. So we have the one resistor available here. Capacitor is connected in order to tune the circuit. This current I1, current I2. M is the mutual inductance between L1 and L2. Eg source is the source weight given by Eg. Rg is the source reactance. The dot is available here. See the dot. The current enters in the dotted end in the first coil. Similarly, current leaves the dotted end in the second coil. So both are different. Current enters in coil 1 at dotted end. Current leaves the dotted end in the coil 2. So the self inductance and mutual inductance are negative, opposite to each other. This is called a parallel opposing. Because of this dot rule we can easily identify. In order to, this is the coil 1, coil 2, E0 is the voltage across the capacitor. So we are going to tune the circuit so that it is called a single tuned circuit. Now we need to go for the mesh equation. By using KVL we need to frame the equation for coil 1 as well as coil 2. So these equations are available here. So we know that the KVL, the applied voltage equal to drop across the resistor and inductor. So Eg is equal to drop across this Rg, drop across R1, drop across L1. Similarly here also. That is voltage rise equal to voltage drop. So based on that, Eg equal to, in coil 1 the Eg is available. Eg equal to I1 Rg. Current in the first coil is I1 into Rg minus, because this mutual inductance is and self inductance are opposing each other. So minus j omega m I2. Right. So I1 Rg minus j omega m I2. Mutual inductance due to the secondary coil current. So that it is I2 equal to Eg. Right, minus omega as for the second circuit, minus omega m I1 for second coil, mutual inductance due to the first coil, so that I1 plus R2 plus j omega L2 minus j omega by minus j by omega c into I2 equal to 0. Right, so this is the equation 2. So we are, this Rg is very much higher, so that we are neglecting the R1 as well as L1. This R1 and L1 is neglected because Rg is, we assume that Rg is much more higher. So that Eg equal to drop across Rg minus drop across mutual inductance. In secondary coil the voltage is not available, 0. So the drop across mutual inductance, R2, L2 and capacitor. So all are available, R2, L2 and capacitor. Here R1 and L1 is neglected. Right. Now we'll go for the further. So these were two equations. Right. We are going to further simplify these equations. Now we'll go for the further details. So the assumptions are available here. Let R1, R2 be the resistance of coil 1 and 2. Respectively, and L1, L2 be the self inductance of the coil 1 and 2 respectively. So the assumption is available here. Assume that Rg is much more greater than R1, much more greater than j omega L1. So Rg is much more greater. So ignore R1 and j omega L1 in comparison with Rg. So that while framing the equation, we are not consider R1 and omega L1. So based on that, the mesh equations are reframed. Now consider the equation 1. I1 Rg minus j omega m I2 equal to Eg. R1 and L1 is not considered. Bring this term that side. So then minus become plus. Now bring this Rg in the denominator. So that we got the expression for I1. Eg plus j omega m I2 divided by Rg. So expression for I1. Now we'll go for the further simplification. So this is the equation 2. Now we'll consider equation 2 minus j omega m I1 plus R2 plus j omega L2 minus omega by j by omega c into I2 equal to 0. From equation 1 we got the expression for I1 that we are going to substitute in the second equation. So this I1 is replaced by the inside equation 2, this I1 is replaced by this equation. Now we can multiply inside minus j omega m Eg by Rg minus j available 2 times j square omega square m square I2 divided by Rg, and this term is available I2. Now this j square is minus 1, j square value is minus 1. So we will go for the further simplification. So minus become plus, it become plus, right. Now we'll take the I2 outside. The I2 available here as well as these two term having I2. So I2 is taken outside, and here one more term is available. That term is brought to that side. So it become plus, minus become plus. Now bring this term in the denominator. So that we got the expression for I2. From equation 1 we got the expression for I1. From equation 2 we got the expression for I2. Right. Now we'll go for the further simplification. So this Rg is multiplied inside. So that this Rg got cancelled. Plus Rg into this term. This term is available. So what happened? Omega square plus m square and this term. Right. So we got the I2 value. So for more further simplified, and we got the expression for I2. Now we'll go for output equation, output voltage. The output voltage E0 equal to I2 into minus j omega c. So this is nothing but the voltage across the capacitor. The current in the second coil is I2. The drop is minus j by omega c. Now we substitute the value. This multiplied and divided by j. So what happened here? This j become j square minus j square I2 divided by j. This stage j is divided here into omega c. We know that j square is minus 1. Already one minus is there. It become plus. So I2 divided by j omega c. In order to bring the j in the denominator, we are multiplied and divided by j. Now I2 minus j omega c now become I2 divided by j omega c. Here negative now become positive. Now we'll go for the further simplification. So E0 equal to I2 divided by j omega c. Split the terms. 1 divided by j omega c into I2. Now we can substitute the value of I2 here. This is the value of I2. In that this j and omega got cancelled. So that what we have Eg into m divided by this c, and the remaining terms are available. Take this equation number 4. So now we got the expression for output voltage E0. I1, I2 values are already available. Now we got output voltage E0 also. From that we can go for the amplification factor. So the output voltage, output transfer function equal to out voltage amplification. That is A equal to E0 divided by Eg. So that is equal here. The Eg is available here. So Eg available. This Eg is brought in the denominator. So it become Eg0 E0 divided by Eg. That is equal to m divided by this term. right? So this Eg is brought to denominator this side, so that E naught divided by Eg, that is nothing but amplification factor. So now we got the expression for amplification factor also. From the output voltage equation we got the amplification factor. Now we'll see, when the secondary side is tuned, that is when the values of the frequency omega is such that, so what is the tuning of the circuit? Omega L2 is equal to 1 divided by omega C. So both are equal means the circuit is tuned together. So brought this term this side in the, so that omega L2 minus 1 divided by omega C equal to 0. So under the tuned condition this expression is 0. So they are available here. Omega j omega L2 minus j by omega. So this term become 0 under the tuned condition. So that this equation 5, based on the above expression, the equation 5 becomes, so this term becomes 0. So what we have, m divided by c omega square plus m square plus rg into r2. This term become 0. Under tuned condition it is 0. So now the amplification function is further simplified, that is under the tuned condition. This amplification factor on tuned condition. You take this equation number 6. Now we'll go for the further discussion. Omega L2 is omega 1 divided by omega C. So multiply this omega into omega, bring this omega here, L2 in the denominator that side. So omega into omega equal to 1 divided by L2 into C. So omega square equal to 1 divided by L2C. This now become resonant frequency, because under resonant condition only this is occurs. So now omega square become omega r square, right? From equation 3, the current I2 at resonance is obtained by putting omega L2 equal to 1 divided by omega C and replacing omega by omega r. So we already got the expression for I2, I1 and E0. Now we are going to obtain the same, we are going to further simplify the expression under the resonant condition by putting this condition, that is otherwise omega L2 minus 1 divided by omega C equal to 0, and also replace omega by omega r, right? So first we will see the current. This is the current, equation 3, this is the current expression. Here under resonant condition this term become 0. So that what we have, j omega r, omega become omega r, m e g divided by r g, omega square m square divided by r g plus this r2. This term become 0. Under resonant, we already know that under resonant condition this term is 0. So I2 at resonant is, this is the expression for I2 at resonant. Earlier what we got, I2 is the normal I2, the current in the second coil. This is the current in the second coil under the resonant condition. Now we'll go for the further simplification. So I at resonance, this Rg is multiplied inside, though this Rg got cancelled. Finally we got I2 at resonance is equal to j omega r m e g divided by omega square m square plus rg into r2. So this is the current at the resonance, current I2 at the resonance. So from equation 6 and 7 it is observed that at resonant frequency E0, I2 and A are depends upon the M, that is mutual inductance, amplification factor, secondary current, output voltage. These three are depends upon the mutual inductance M. The maximum value of E0 or A depends upon M. So if you want to find out the maximum value of output voltage or amplification factor means that is depends upon the M value. So that to get the condition for maximum E0, we need to differentiate the equation E0 with respect to M, because E0 is depends upon mutual inductance. Then by equating the 0 we will get the condition for maximum output voltage. Maximum output voltage depends upon M, so that it is differentiated with respect to M, or the E0 is differentiated with respect to M and equated to 0 to get the maximum value for E0. Now we'll see, now we'll substitute the E naught value. So d by dm E naught equal to 0. E naught is nothing but EgM divided by C of Rg R2 plus omega R square into M square. Now we need to differentiate this term with respect to the M. M available in numerator as well as the denominator. So we can use the formula U by V method. This is U and this EgM is U. This term available in the denominator is the V. What is the formula differentiation? V du minus U dV divided by V square. V into differentiation of U minus U into differentiation of V divided by V square. So this is the term U and this is the term V. Now we'll go for first substitute the V. This is the V. Then du. So I see U, we have to differentiate with respect to M. So M divided by C, while differentiating this M is equal to 1. Differentiation of dm is 1. Differentiation of x is dx. Integral dx is x. Similarly here this dx, M is the differentiation of M is 1. So Eg divided by C into 1 minus U. The term U is substituted as it is. Then dV, we have to differentiate this term V. So here this term is constant, so it becomes 0. Here M square is available, differentiation of M square is 2M. Then that is equated to 0 divided by V square. This is V square. Now we'll go for the further simplification so that we'll get the condition for maximum output voltage. Right. So this term is Eg divided by C minus this term is 0, so that we have 2m into omega R square divided by V square. This V square is equal to 0, so this term, while multiplying this term with 0, it becomes 0 only. So after that we got this expression. Bring this term that side, so that negative become positive, it become plus. Now Eg available on both the side. Eg available, C also available on both the sides, so got cancelled. Rg R2 plus omega R square M square equal to 2M square omega R square. So these two terms are very similar, so brought this term that side so that it become negative. So 2 times M square omega R square minus 1 times omega R square M square, so it become 1 time. Right? I will go for the further simplification. So that Rg R2 equal to M square omega R square. Bring this omega R square in the denominator, this side. So that M square Rg R2 divided by omega R square equal to M square. So that M equal to Rg R2 divided by omega R square. Now take square root on both the sides, so that M equal to square root of Rg R2 divided by omega R. So this is the value we got. So when M equal to square root of Rg R2 divided by omega R, the output voltage is maximum. So this is the condition. dm, d E naught divided by dm is equated to 0. At the time we got this expression M. So this is the value at which the output voltage is maximum. So by substituting this M equal to this value, we will get the maximum output voltage. Now we'll see how we are getting the maximum output voltage. So this is the expression for output voltage E naught, EgM divided by here. So here we need to substitute M equal to Rg, square root of Rg R2 divided by omega R. So that is the condition at which it is maximum. Similarly, this here also it is substituted M square. But this term at the resonance, this term is 0. Omega j omega L1 L2 equal to minus j equal to j omega C. So when brought this side, this term is 0. So that Eg square root of Rg R2, this omega R is available in the denominator, right? C into omega R. Then this term is available. While taking the square, it become Rg R2. Square root of Rg R2 square is Rg R2 divided by omega R square into omega R square. Now everything is converted. Omega is changed into omega R, resonant condition. This term is 0. So Rg plus Rg into R2. this omega r got cancelled. So what we got finally, Eg square root of Rg R2 divided by C omega R 2 Rg R2. So that is nothing but Eg. So here the square root of Rg R2 available, here Rg R2 available. So we can write like this. For example, the root 3 can be written as multiply and divided by another root 3. So what happened, root 3 into root 3, 3 divided by root 3. So based on that we can have this formula, right? Square root of Rg R2. So finally we have Eg divided by 2C omega R into square root of Rg R2. So this take equation number 9. So this simplification based on root 3 divided by 3 is available. This root 3 divided by 3 can be written as root 3 into root 3. So this root 3 got cancelled. We have 1 by root 3. Not based on this. This is based on this expression. Root 3 divided by root 3. So square root of Rg R2 is root 3. Rg R2 is a 3. Right? This 3 can be written as root 3 into root 3. Root 3 into root 3 is again 3. So this root 3 got cancelled. We have 1 by root 3. Rg R2. Now we'll go for the further simplification. Now we'll see the maximum amplification. So far we got the maximum output voltage E0. So this is the expression for amplification. In that we substitute m equal to root 3 into root 2 divided by omega r. If you substitute that value, we will get the maximum amplification, right? So this m is not replaced. Only this m is replaced by square root of Rg R2 divided by omega r, right? So we'll go for the further simplification. Square root of Rg R2 omega r into C Rg R2. So here also now substituted square root of Rg R2 divided by omega r the whole square. Now we'll go for the further simplification. So square root of Rg R2 omega rc into Rg R2 plus omega r square. It is while taking square root, this square root become normal Rg R2 divided by omega r square. This omega r square got cancelled, right? So we have this is Rg R2, this is also Rg R2. So 2 times, we have 2 times available. Square root of Rg R2 divided by 2 times of Rg R2 and omega r c, right? Similar, very similar to previous case, the square root of Rg R2 divided by Rg R2 can be written as 1 divided by square root of Rg R2. So this is the maximum value of amplification. Am is nothing but 1 divided by 2 omega rc square root of Rg R2. Now we'll see the maximum value of the current. By using the same procedure, you can find the maximum value of current. So this is the current expression. In that we are going to substitute this 2m, we are going to replace square root of Rg R2 divided by omega r. So here also, right, here square is there. So while taking the square, it become Rg R2 divided by omega r square. This omega r square got cancelled. So finally what we have, j Ej Rg square root of Rg R2 divided by 2 Rg R2. Very similar to root 3 divided by 3. It is 1 divided by root 3. Like that, Eg divided by 2 square root of Rg R2. So this is the value of maximum value of current by substituting the m. So we calculated the maximum value of the m, the condition for maximum. For that we got the expression for m, mutual inductance. That is substituted in 3 different parameters. Output voltage E0, amplification A, and current I2. So that we got the maximum value of output voltage E0, maximum value of amplification, and maximum value of the current I2. Now we'll go for the further. These maximum values are obtained by substituting m equal to square root of Rg R2 divided by omega r in expression E0 A I2 at resonance. So we know that m equal to k square root of L1 L2. By changing the coupling factor k, we can vary the m. This variation of amplification factor or output voltage with the coefficient of coupling. So by changing the K, we can change the M value. So that this variation can be done by changing the coupling of coefficient of coupling, this K value. So these three are based on the M, but M is based on the K value. So by changing the K value, we can vary the amplification factor with the coefficient of coupling. So based on that, the graph is available. So x-axis is the resonant frequency, y-axis amplification factor. So this is the for different coupling coefficient of coupling, right? So these maximum values depends upon the mutual inductance M, but mutual inductance based on coefficient of coupling. So for the different values of coefficient of coupling, the graph is obtained. So K equal to here K1. K1 is maximum. K2 is less than K1. K3 is less than K2. So accordingly we got the amplification also. K1 is the maximum value. We are getting maximum amplification. K2 is lesser. So the amplification factor also lesser. K3 is very lesser. So the amplification factor also lesser. Right. So when K value increases, the amplification factor also increases. Initially it is slowly increases, at this point reaches maximum, thereby decreases. For different values of coefficient of coupling, we got the different curve, right? When the coefficient of coupling increases, the amplification also increases. So in this video we discussed the single tuned coupled circuits, connecting capacitor at the secondary circuit in order to tune the circuit. We got the expression for E0, I2 amplification factor, thereby maximum value of these three parameters. Finally we draw the graph also. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening.